forget, as I keep doing, but I remembered now. Yay. A couple of announcements. Number one is when you have a question for me, I truly do appreciate when you email me with your questions. One thing that I'm going to ask for you to do, if you're not using Canvas to email me, which is fine. We love it when you use your Iowa Lakes email. That's what we're encouraging you to use even more than Canvas, but Canvas is fine too. If you aren't doing it from Canvas though, please remind me of which class you're in. You could either just say Math for Liberal Arts in the afternoon. That works. You could say 110, 102. That works. But I have 4 different courses and I have 3 sections of Math for Liberal Arts and 2 sections of the other one. And I don't remember who's in what class. So when you tell me, will you please check on the quiz for me? I will gladly do that. But right now, all of my classes literally have quiz 1 due. And so when you tell me it's quiz 1, it takes me longer than I would like it to take me because I don't always know which ones are in what classes right away. So I'm going to apologize for that, sort of. But if you could just say, hey, I'm in your afternoon MLA class or in 110, 102. No more than a few characters, and it will help me a whole bunch. And I would really, really, really appreciate that. That would make my life even easier, which I would appreciate. Speaking of which, Chapter 1 homework is due the end of the day today. So is quiz number 1. Remember, there is that grace period built in. So if, again, you're running late and it's like 10 o'clock at night and Canvas goes down, don't worry about it. Don't panic. Just do it tomorrow morning. If you have an issue with the homework, a couple of people have had, in 2 different classes, have had one issue with a quiz question where they couldn't see the images on it. My best advice in a case like that is to reload, log out and reload and see what happens. So if you reload and it says you've used up all your quiz attempts, send me an email and I'll reopen it for you. If you reload and you still can't see the pictures, do not take the quiz. Contact the help desk and see if they can help you figure out why those images aren't loading. It's not happening to everybody, as far as I know, and because I've literally heard from one person in my online only Math for Elementary Teachers class, and I've heard from one person in one of my other classes. In fact, it may have been this one, where that happened, but I haven't heard it from anyone else. I don't think it's a quiz issue on my end. If it is, obviously I will do whatever I can to fix. I will fix it if it's on my end, but I would love to know what's going on with that, because that's new. Even last semester when we did stuff on Canvas, and I used Canvas a little bit even before we went all online, I didn't hear about those issues, so I'm not sure what's causing them. In my past experience, for me, sometimes it's been a hiccup with my internet connection while it was downloading or something. One person at least said that certainly couldn't be the case for them, which is fine. I just don't know. So try reloading, and that doesn't work. The next thing you should do is contact the help desk. If the help desk gives you good advice that gets it to work, please share that advice with me, and I will share it with others so we can solve these problems. You will not be punished for not being able to see the images as long as I know about it. That will not be held against you, obviously. So stuff due tonight. Again, the practice for chapter 2, we started chapter 2 last time. That is up here. That's available. Again, there's a lot for 2.1. If you happen to have looked at it at all, you know there's a lot for 2.1. There's a lot in this section, and a lot of it is newish, or as we talked about last time. So we're going to keep going with 2.1 though today, and continue talking about some basics, introduction to set concepts. And we ended last time right about here. Yes, right about here, where we talked about different methods for representing sets, if I remember right. And so we can do it in words, we can do it as a roster, and we can do it using, actually, maybe we didn't end here. Maybe we actually ended here. I think we maybe didn't get to this slide. Whether we did or not, I will start here. It'll be review or new, depending on. There are three major ways we can describe what belongs in a set in this course. There's actually a fourth way called interval notation, which we use a little bit in finite math. You probably would use it in college algebra, but we aren't going to use in math for liberal arts. So one way is using words. So we could say that set W is the set of the days of the week. We could say that set L is the set of letters in the alphabet. Set S is the set of students in math for liberal arts. Set C is the set of counties in Iowa. So we could just use words to describe what are members of a set. Often we want to actually list who the members or what the members of a set are. That's called the roster method. Just like a roster of a team is a list of the players on the team. The roster of a set is a list of the members or the elements of the set. So if we were doing this in the roster method, we would see that set W equals, and then we put in braces, and we'd actually list the days of the week. Or if it were set L, we would list the letters of the alphabet. We don't have to actually list all the letters of the alphabet. We'll get to that in a minute. But in some cases, it's something that we would have to list everything. We'll talk about how to make that doable in cases with lots of entries. The final method we're going to talk about in this course is called set builder notation. Sometimes that's just abbreviated as set notation. That's kind of the most complicated. It looks the funkiest, but it's also the most powerful. It's the most compact in many ways. It's the most useful in many ways. It is something that shows up in lots of other math courses, especially as new concepts are being introduced. So it's something that's really helpful to me to understand how it works a little bit. So the big three methods. So we have examples here of word and roster. We're going to see an example of this in set builder notation in a couple slides. So one thing that we do is we might, for the same set, be given it in one form and asked to write that information in a different form. So here we're given a set. The set P contains the elements Washington, Adams, Jefferson, Madison, Monroe. And we're asked to write a word description of the set. So we're given a roster, and now we're asked to describe it. Now this may or may not be tricky for you, depending on your knowledge of early US history. In this case, it depends a lot on background knowledge. That's why word descriptions, that's why different methods are better for different situations. So a person might look at these and think a whole bunch of different things. They might think, oh, these are last names, which is true, they are last names. But there are many, many other last names in existence. There aren't just these 5. And the thing about this is that these are the only 5 members of this set. There's nothing else that can join it. So it can't be last names because there's more than 5 last names. Similarly, someone might say, oh, they're the names of cities or of counties or of townships, and they are certainly the names of cities, and they're probably also the names of counties somewhere and townships somewhere. But again, there are other city names that aren't in this set. There are other county names or township names or whatever that aren't in this set. And the description of the set has to be precise. Remember our definition of a set way back on slide 2. Oh, I gave you the solution. Is that a set has to be well defined. And so that includes the words we use if we're using words to describe a set. Here, set P is the set of the first 5 presidents of the United States. So there are 5 elements in this set. There were 5 presidents of the first 5 presidents of the US. Those are the only things that belong in the set. And there is no other, I don't think there's any other way we could describe that set where only those 5 things are present. Or we might be given the set in words and then asked to use a roster method to write the set or to represent the set or to express the set. So we in words have set C is the set of US coins with a value of less than $1. Express this set using the roster method. Where express here means, to write it, to show it. So we would have C equals and then a brace. And then we would just list the names of those US coins. We're going to assume that they are current coins. They aren't like half pennies or anything from colonial times or anything like that. So penny, nickel, dime, quarter, half dollar. Those are the current US coins that have a value of less than $1. And again, some people might call a half dollar a 50-cent piece or something like that. That's still correct. That wouldn't be an issue. So the US penny doesn't actually have the word penny on it, if I remember correctly. And so same thing, if someone instead of penny put the 1-cent piece or something like that, that would still be right. But we usually just refer to it as a penny, even though that word doesn't appear on the coin itself. Again, it doesn't matter what order items in a set are listed in, other than trying to make it easy on your reader. So here, we're being systematic. We're going from the smallest value to the largest value. It would also make sense to go from the largest value to the smallest value. That both helps your reader. It also helps you in double checking and making sure you haven't missed something. If we have just numbers in a set, we usually want to write those in increasing order, like 10, 11, 12, 13, rather than writing them randomly. Often, if we have letters in a set, we want to put those in alphabetical order too. But again, it doesn't matter, technically. Same thing for our set of presidents. I mean, this is the order they were president in, but those 5 names can come in this set in any possible order. We could have done Jefferson, Monroe, Washington, Madison, Adams if we wanted. It's the same set. But it makes more sense to put them in the same set that they held office in. It makes it easier for us to double check. It makes it easier for our reader to recognize what it is when they see it as well. All right. Back to set builder notation. I promised we would come back to that, and I keep my promises. So this is an example of that earlier days of the week set W, written in set builder notation. And under it, in those word balloons, we are saying exactly how you read it when you see something like this. So when you see something like this in your textbook, when you're reading it to yourself, in your mind, what you're saying is, set W, that's what the capital W stands for, is the set of. So capital letter is the name of the set. So set W in this case. Equal sign here is. I sometimes will use consists of instead of is, but is just fine. And then this opening brace, which is sometimes called a left brace, we would read that is as the set of. So set W is the set of. That's going to be followed by some variable. The variable you're going to see most often is the letter X. And you probably remember that from high school algebra, that often if we need a variable, our go-to variable is X. It's the most commonly used. It's the same thing here, but it could be any letter. It could be V, it could be T, it could be Q, it could be A. It could be a Greek letter like alpha or beta or gamma or theta. It could be a Hebrew letter in certain circumstances like the letter aleph. Normally, it will be a letter from the Roman alphabet that we use. Rarely, it will be a Greek letter in some math classes, and rarer still would it be some other character from some other language. If those other elements are used, they are used in those types of math for other things as well. So we use X a lot. but it can be any letter that represents just a generic variable. So when we read this as all elements X, this next character is called a pipe, and it looks a little bit like a vertical line segment. And sometimes people will call it a vertical line, and that's fine too. This character is on your keyboard. It gets moved around a little bit. But if you have if you're on a PC, it's sometimes in different places on a Mac keyboard, but on a typical PC keyboard, it is going to be actually often very close to where the braces symbols are. So on my keyboard, for example, I have my brackets and brace keys. And then right next to that, I have the backslash key. And if I hit shift and backslash, I get that character right there. And on my keyboard, those happen to be right above the enter key. But again, this can be in a different location on different keyboards. I've had other computers where it was moved around a little bit, but it is there. And I'm fairly certain it's there because this pipe symbol, especially back in the day, was used a lot in computer programming, which is why it's actually on the computer keyboard at all, which is helpful because we use it in set builder notation also. We read this symbol as the words such that. So set W is the set of all elements X such that X is a day of the week. This last part is the criteria for X to be part of the set. Think of the criteria as like a bouncer somewhere. Saturday comes walking into the club. Bouncer says, "What's your name?" And Saturday says, "Saturday." The bouncer says, "Come on in." Tuesday comes walking in. Bouncer says, "What's your name?" "Tuesday." "Come on in." Now January comes in. Bouncer says, "What's your name?" "January." "Get out." 17 comes in. Bouncer says, "What's your name?" 17. "Get out." Only days of the week can be part of the group. Only days of the week can be in the club. That's what this is telling us. This is telling us that only if X is a day of the week can X come into the club. Can X be part of the set? So if X is a month of the year or a number or something else, anything other than a day of the week, it's not part of the set. That's what makes the set well defined. Here's another example. In Word, set A is the set of all even numbers. So here I used a different variable than Y, just so we would get some variation, or a different variable than X, sorry, a different variable than X, just so we get some variation. So we would read this as set A is the set of all elements Y such that Y is an even number. Okay, and you don't have to read it exactly like that. Like I'm not going to, quiz you, give you an oral quiz saying, here, you must read this correctly. But this does get used a lot in other math courses. So if your future plans include courses beyond math or liberal arts, you will likely see terminology like this used. And the more you can get it in your mind, the easier those courses will be for you, I think. So again, you could, something like set A consists of the set that's all elements Y such that Y is an even number. So again, that means, think going into the club, if 2 comes in, 2 is welcome to the club, but 3 is not. -7 is not. 0.2 is not. 18.5 isn't, but 18 is. Only even numbers are allowed in. Or vowels. Now, this is actually not really well defined because people are linguists or people who study language, and linguistics, because I'm a nerd, linguistics is one of my hobbies. Like I love linguistics. If I could get an online master's degree in linguistics somewhere, I would probably do it because it fascinates me. So you're going to be stuck with linguistics examples on occasion, which I'm kind of apologize for and kind of don't. So linguists argue about what a vowel is, but typically back in elementary school, if you went to school in the US, you learned probably that the vowels were A, E, I, O, and U. And some of you may have learned and sometimes why. Linguists have lots to say about things like that. We're going to assume that vowels in English are A, E, I, O, U, and we're going to ignore why. There's actually arguments about W for reasons I'm not going to go into in a math class, and other things as well that go. There's all sorts of things like what makes a vowel and a consonant, other things that are interesting, but sadly we aren't going to talk about. So if we're interested in vowels, again in English, in set builder notation, we have here set V is the set of all elements G such that G is a vowel. Again, I'm using G here just as a different variable. It's not a good variable to use when we're talking about vowels probably because it's going to confuse people since G isn't a vowel and stuff like that, but that's okay. Notice though, I use this for both these cases, excuse me. The variable does not have to be the lowercase version of the set name. So we have set A, capital A, but our variable is Y. We have set V, capital V, but our variable is G. The variable does not have to be the same letter as the set. In fact, it usually isn't. It could be, but it usually isn't. All right, let's put all three of these examples together, all three types of sets together. Words, rosters, set builder. So in words, set P is the set of US presidents who died in office. The roster method would be a list of those people. So we would see here capital P equals Zachary Taylor, William Henry Harrison, Abraham Lincoln, James Garfield, William McKinley, Warren G. Harding, Franklin Delano Roosevelt, and John F. Kennedy. And again, this list could be in any order. This happens to be in the order that they held office because that's the easiest way for me to remember that I got everybody. And then set builder notation. The set P is the set containing all elements X such that X is a US president who died in office. So any of these people are part of the set, but there's no other person who is part of the set. Now, when we're dealing with real world scenarios, like not with just numbers, but with, stuff like this, it is certainly possible that this set, someone else might get added to it. Like whoever is president in the year 2097 might have a heart attack and die in office. And so whatever that person's name is would be added to this roster. So a roster here isn't necessarily complete when it's, something historical or social or cultural, because those things can change over time. But the set builder notation is complete. This would cover it for as long as there is an American presidency. We might sometimes be asked to go from set builder notation to roster notation. And so here we want to express this. Set A is the set of all elements X such that X is a month that begins with the letter M. And so to put this in roster notation, we would first write a capital M, an equal sign, a brace, not a parenthesis, and then we'd write our months. There happen to be 2 months that start with March. 2 months that start with a capital M, March and May. And then a closing brace. The closing brace is honestly the #1 place where I mess up, even as I do examples in class. I want to put a parentheses at the end because we're so used to doing that. So I share that in case that also applies to you. Like I'm really good about starting with the brace, but especially if it's a long list, at the end, I'm really likely to just put this and then think, oh, shoot, I don't want to do that, and quick draw on my brace. It's almost like I've got caught in that in homework in the past and gotten points taken off. So again, here we have it. Oh, sorry, not M. My bad. The set is A, not the set is M. Sorry about that. And again, the letter that a set is called doesn't really matter, just like a variable we use doesn't matter. In some cases, an author will use a letter that represents something, like they might use M for month or M because we're dealing with that letter. They might use W for week or P for president. They don't have to. You will, for set C, A and B use the most often, capital A and capital B, just like you see that used, just like you see X and Y used the most often for variables in algebra class. They just are sort of by convention. If we don't know what we're going to name a set, we usually call it capital A. And if we used a bunch of capital A's, we throw in a capital B here and there, just like here. So I mentioned before that sometimes we have to list a really long, there's lots of members of a set, like letters in the alphabet. There are 26 letters in the English alphabet. If you were listing all the letters in the alphabet in a set, you could certainly do it. I mean, you've written all 26 letters, but it would take you kind of a long time. I mean, not a real long time, but it would take you a while. It'll get annoying. We can use ellipses. So you've used ellipses in writing classes. We use ellipses in writing when we are taking a quote from somewhere and we're leaving words out of the quote, for example. And ellipses, again, is a series of 3 periods. Each one has a space between it. And we sometimes just call it ... I call it ... but they're really 3 periods. So in a case like this, first one you see here, where set A has these elements in it, and we go 5, 6, 7, 8, 9, 10, and then ... That means it keeps going on in this pattern. So it keeps adding 1 each time. So we would go from 10 to 11 to 12 to 13 to 14 to 15, and we'd keep going like that until we reached infinity, which we would never reach, because remember, infinity is not a number. Maybe I haven't gone over that in this class, but infinity is not a number. It's a label. It's an idea. So in words, we could say that this set is all whole numbers. We'll talk about what whole numbers are in a couple minutes, that are equal to or greater than 5. And we have to use ellipses here because we can't write all of the numbers bigger than or equal to 5, or all the whole numbers, because that list goes on forever. Ellipses are also used to show a pattern goes on within a set. So here we have set B is these numbers. We have 2, 4, 6, and then ... ellipses, and then 18, 20. And so here, when we see this in writing, we have to use inductive reasoning, like we started the course with, in order to figure out what the pattern is. Same thing if we're putting this down, we have to use sort of reverse inductive reasoning, I guess you could say, to give our reader enough clues so they know what the pattern is. You want to put at least 3 numbers in a pattern like this before the dots. Sometimes the examples in your book will use 4, and that's fine. Using more than 3 is fine. I often like to put 2 numbers at the end instead of just 1. Your book might have put this as 2, 4, 6, 8, ... 20. Either way is fine. Either way you would get credit for it. You just need enough of a pattern so that your reader is clear that we're adding 2 each time. We aren't multiplying by 2 each time, or we aren't, doing something else each time. So this is multiples of 2 between 2 and 20 inclusive, which means it includes 2 and 20. You could say it's counting by 2s until we get to 20 also. That's sort of the everyday way of saying this. So in a set, when we use when we use roster notation, the ellipses mean that pattern is continuing. If it's at the end or the beginning of a roster, it means it goes on towards infinity if it's at the end, or negative infinity if it's at the start. If it's in the middle of it, it means the pattern just goes from, it starts at 2 here and it ends at 20. Any questions so far? Okay. Another example where we would use ellipses is we talk about integers. Well, we will talk more about integers later in the course in chapter 5. Remember that integers, if the whole number, if we have numbers like 1, 2, 3, and we aren't dealing with fractions or decimals or anything like that, if we take their negatives, like -1, -2, -3, and we also have 0 involved there, these are the integers. And in fact, the letter Z is used usually to represent this set because Z, I believe in German, Z is the first letter in the German word for integer, if I remember right, which I think is Zahle or something like that. So the ellipses at the beginning, and there should really be a comma after them, I think, indicate that this list goes on towards negative infinity on the number line. So this goes all the way towards as small of a number as you can imagine, negative trillions upon trillions upon trillions. The ellipses here means it goes all the way towards positive infinity, as you can imagine. And each time it's either going up by 1 as we go towards positive infinity, or it's going down by 1. So again, this is the bouncer at the club is looking at this condition. If the number 22 comes in, they're like, yep, you're fine. The number -1,000 comes in, sure thing. But if pi comes in, no, because 3.1415, etc., is not an integer. If 1/2 comes in, no, that's not an integer. But if -2 comes in, that's fine. So the ellipses here tell us that this pattern keeps going on in whatever the direction is. If it's at the start, it goes on towards negative infinity. If it's at the end, it goes on towards positive infinity. I think I talked about infinity in my finite math class this semester. So you know, if I haven't mentioned it before, infinity is not a number. It is simply an idea. It's a label. You could never count to infinity because no matter how big of a number you get to, you can add 1 to it and get a bigger number. Or for that matter, you could multiply it by itself and get a bigger number. Or you could raise it to itself as an exponent and get a bigger number still. Same thing for smaller numbers. No matter how small a number is, you could subtract 1 from it and get a smaller number still. Or you could subtract 1 trillion from it and get a smaller number still, and so on and so forth. So infinity is not a number. It is just a label. It's just an idea. It's a concept. We'll talk more about concepts in a minute. One particular type of set that's important is called the empty set. The empty set has 2 names. The empty set is also called the null set. So you might see either term used. We use empty set much, much more in this class. And in general, I think the empty set is used more often in most math courses, especially introductory math courses. An empty set is a set that contains no elements. It has nothing inside of it. So in our previous example, there were a bunch of presidents who died in office. But until Zachary Taylor died in office, or until Taylor? Did I put those in the wrong order? Oh, that's embarrassing. I think I put those in the wrong order. Until Harrison died in office in 1840. I did put them in the wrong order. Shame on me. There hadn't been any presidents who died in office, so that would have been an empty set. The number of months in English that start with the letter Q is an empty set. The days of the week that start with the letter B is an empty set in English. So an empty set is a set that contains no elements. It doesn't have anything in it. We can represent the empty set in one of 2 ways. You can represent it with 2 braces with nothing inside of them. Now, if you're typing this, it's okay if you put a space inside them, like if you type brace, space bar, brace, because otherwise they tend to run together and look like a funky symbol on their own. But other than that, there's nothing inside of them. If you're typing something in Canvas, this is what you should normally use. If you're writing something by hand, or if you're using an equation editor, either in Canvas or Word, you can also use the null symbol, which is this symbol right here. This is not the number 0. This is not the number 0. This is not the number 0. Is this the number 0? No, good answer. Thank you for shaking your head. Not the number 0. It's completely understandable that people think it is, because on lots of computer keyboards, for example, including on mine, I just double checked, that's what the 0 key kind of looks like. It's not quite as round, but the 0 key looks kind of like this on my computer. And some of you, maybe not you in this class, but out of all of my classes this semester, I'm willing to bet that at least one student, when they write 0 in their work for a class, they write it like that. You should not do that anymore in college math classes, because this means null. And it's also tricky because there are actually languages, I think in some of the Germanic languages, other than English, languages that are related to German, the word for 0 is really is like null or null, very similar. So it's also confusing there. The reason that this is 0, the symbol for 0 on your keyboard, is to keep it so we know it's not the capital letter O. And that has to do with typewriter keyboards from way back in the day, more than 100 years ago now. When the first typewriter keyboards were developed, there wasn't usually a key for the digit 1. A lowercase l was used instead. And there wasn't a key for 0. A capital O was used instead originally. That changed over time. And one reason it changed is when computer keyboards started being developed, there had to be a key for different characters, because obviously in programming, the digit 1 and the letter L, very different. The capital O and the digit 0, very different. So you need distinct keys. And that moved over to typewriters. Like if you went and bought a regular typewriter today, there's still some being sold. It would have a digit 1 and a digit 0 on it. But if you went to an antique store and saw a calculator from, the 1920s or the 1910s or before, they would not. And so on early keyboards, this symbol was used partially just to differentiate the keys. But you should not use it when you are writing. And again, it's completely understandable, because if I were just putting this, you would not know if it was a 0 or a 1, because I might go, oh, it's a 0, or I might go, oh, it's an O. They look the same in everyday writing if it's by itself. But from context, we can tell it isn't. So this is the symbol for the empty set. It's called the null sign, or the null symbol. It is not the same as 0. It's also confusing because there are some languages where this is actually a letter. There's an O with a line through it like this, and it's one of the letters in their alphabet. So it's confusing that way too. Okay. So that's my rant on that. A couple of examples of empty sets. This first one is really tricky. So I'm glad it's first in a way, because we get the hardest one done right away. These are all sets that don't have any elements in it. So you have to think really carefully in math about this word and. The words and or in math aren't always used exactly the same way as they are in everyday speech in English. What this means in math is and means both at the same time. So again, we're thinking of the bouncer at the club. You can get into the club if you're a number and you are both less than 4 and at the same time greater than 10. So the number 3 walks into the club. The bouncer says, wait, are you less than 4? And 3 says, yes, I am less than 4. The bouncer says, are you greater than 10? And 3 says, no. And the bouncer says, get out. The number 15 comes into the club. Bouncer says, are you greater than 10? Yep, I'm 15. Are you less than 4? No. Get out. There's no number that's both less than 4 and greater than 10 at the same time. That's what and means. Both conditions have to be met. And so this is an empty set. No numbers belong to this set. Here, we have the set of all elements x such that x is a fawn that speaks. A fawn is a baby deer. We're going to presume this is in the real world, and we are not talking about Bambi. Okay, we are not talking about cartoon deer. And so, as far as we know, there are no baby deer who actually speak. And so this would be another example of the empty set. It has no members. Now, maybe a trillion years from now, deer will evolve the ability to speak, and that will no longer be an empty set. Or maybe somewhere in some deep woods somewhere, there is a group of deer that can speak due to mystical means. And then that would no longer be an empty set. But as far as we know, there are no speaking deer in the real world, fawns or otherwise. I mentioned last time, I think, when we talked about problem solving, that I don't like to use trick questions. I don't intentionally do trick questions. Some of what you're going to see on these slides could be considered tricky, and I want you to be aware of that. So I'm not going to make you answer this out loud or in chat or anything. I just want you to think about it as we go through it. We're going to look at about 5 examples, and we're going to see if these are the empty set or not, and why they are or are not the empty set. So our first example, A here, is this. And again, you don't need to answer. In fact, don't answer. Just think, is this the empty set? No. This is a set with an element in it. That element happens to be the number 0. This is not an empty set. How about this one? Again, no. This is a number, not a set. This is just the number 0 hanging out on its own. Neither of these are the empty set. Here's a tricky one. I mean, all of these could be considered tricky. Is this the empty set? Again, the answer is no. This is a set that contains the empty set. And I like this analogy that a math professor I had once used with us. Think of this as a box that has an empty box inside of it. So a set, right, is a collection of something. So we might keep our collections in a box. So rather than a collection of, Hot Wheels cars or something, we in here have a collection of different objects. That collection could be of numbers or of letters or of shapes or of colors or whatever. Now in this box right now has nothing inside of it, so it's the empty set. If instead inside this box I put another box, but that box is itself empty, now I don't have an outer empty set, I only have an inner empty set. So this is a set that it contains the empty set. Tricky. That's why we're going over in class rather than just showing up on a quiz. C is really similar to the problem we saw at the start of this stuff on the empty set. But there's one important difference. Here, instead of the word and, we have the word or. Or in math is used a little differently again than it is used in everyday English. Or in everyday English is ambiguous. It involves choice, but sometimes your choice is to do one or the other only. Other times your choice could be to do one or the other or both. So if I were your advisor and I asked you, hey, next semester, do you want to take statistics or do you want to take US history? You could reasonably say, I want to take statistics. You could reasonably say, I want to take US history. Or you could reasonably say, I want to take both. And any of those would likely be entirely acceptable solutions or answers. On the other hand, if you are going to eat somewhere and they say, oh, would you like soup or salad? And you say both, they are going to charge you extra, right? If you're asked, do you want soup or salad? The implication in typical English is you're choosing one or the other, not both. So our word or in English is ambiguous. It could be used a little differently. There are actually languages where they have different types of or for those different situations. There's one or if your choice is this, but not both. And there's an other or if you could choose this, or both of them. So in math, we always use what's called the inclusive or. And so the inclusive or in math means I could choose A or B, or I could choose both A and B. And here, or means that now, if 3 comes up to the club and the bouncer asks, are you less than 4? And 3 says yes, the bouncer says, come on in. 3 says, wait a second. That other club, they asked me if I was greater than 10 too. And what the bouncer says is, it doesn't matter. You can be either less than 4 or greater than 10. Either way, you get in the club. 15 comes in, same thing. Are you greater than 10? Yeah, I'm 15. Oh, come on in. Wait a second. That last club, I couldn't. Well, that's because that was the and club. You had to be both. Here you can be either. Now, if the number 7 shows up, number 7 is still out of luck because 7 isn't less than 4 or greater than 10. So it still gets tossed aside. So this, and this should really be D, not C. I added C to the other slide. This is not the empty set then, because any number less than 4 can be part of the set, and any number greater than 10 can be part of the set. Let me see that there. And then finally, the set of all x such that x is a square with 3 sides. Well, let's draw a square with 3 sides. There's side 1, there's side 2, going good. There's side 3. Oh, wait. Darn it. Try it the other way. Side 1, side 2, side 3. Ah, darn it. Obviously, by definition, a square has 4 sides. So this is the empty set. It doesn't exist. You can't have a square with 3 sides. Just like you couldn't have a triangle with 7 sides or a hexagon with 2 sides. Squares need to have 4 sides. Exactly. So this would be the empty set. No squares exist that have just 3 sides. Questions? Okay. I want to introduce a couple of different characters to you that we use when we deal with sets. These come from the Greek alphabet. These are the Greek letters, sort of the Greek letters for epsilon, which is where our letter E comes from. And much like this looks a little bit like an E, almost like when some people will write really, they might write their capital E like this. And so it's kind of like an E that's just kind of been extended a little bit. Looks a little bit like the symbol for the euro currency also. This symbol means element of, and that's what we read when we say it. An element of a set. So January is an element of the set months of the year. Or if set E was the set of even numbers, 2, 4, 6, 8, we would say that 10 is an element of set E. If we put a line through that E, going from the top right to the bottom left, like this, that means not an element of. So 10 is an element of the even numbers, but 7 is not. 7 is not an element of the even numbers. And remember, element and member mean the same thing. Element is the more mathy term than member when we talk about what's in a set. So the items that a set contains are called its elements. If something is an element of a set, we use this funky E symbol. And if something isn't, we use the E symbol with a line through it. There's not a good way to write this on your computer keyboard if you're ever doing something that way. You can get to this symbol in equation editors of different types or in symbols in Word and stuff like that. When it shows up on things like quizzes in Canvas, I don't make you write it. I use a matching thing, like which of these symbols goes in the blank, and you'll choose it from, A, B, C, or D and stuff like that. But if you're doing it by hand for homework or something that you're taking a picture of, you just write them out like this. So we're going to see with a couple of examples here. A couple of them are straightforward and some of them are a little trickier, whether the statements are true or false. So this first one, we would look at this as saying something. So first of all, what is this? What is this set that I've circled?
Alphabet.
That's right. That's the alphabet, the letters of the alphabet. And so our question is this a true statement? R is an element of the letters of the alphabet. Yeah, that's true. R is a member of the letters of the alphabet. Here we would say this as 7 is not an element of the set of the numbers 1, 2, 3, 4, 5. Also true. 7 is not part of this group. Now, on the other hand, if we would have had this, we would say 7 is a part of this set because this is 1, 2, 3, but those numbers keep on going forever. So it would make sense here that 7 is a set of this, or 7 is an element of this set. C is the tricky one. Set A is an element of set A, comma, B. This is false. Set A is a set, and it is not an element of this other set. And this is tricky because we're going to talk next time, probably next time, about subsets. And it gets interesting at times. But this one is pretty straightforward. This is a set that contains two elements. It contains A and it contains B. So it would make sense to say that A is an element of the set A and B. And in fact, A is also an element of this set. A is an element of the set that contains just A. But this is not an element of this. So we would write, to be true, we would change this to is not an element of. Questions? All right. One particular important set of numbers I want to talk about is the set of natural numbers. You see at the top of the center of your screen here from your book, the set of natural numbers, and you see a capital bold-faced N equals 1, 2, 3, 4, 5, dot, dot, dot. The natural numbers are also called counting numbers, and they're called both natural and counting for the same reason. These are the numbers that people learn when they learn to count. When you were a little kid and you first learned to count, you learned to count eventually 1, 2, 3. Now there's all sorts of steps that are involved in learning to count, including figuring out order and stuff like that. This is probably also true from when numbers were first invented. That in the real world, numbers are abstract. You cannot look out and say, oh, look, there's a herd of 3 galloping in the pasture. Oh, I see a 4 in the sky. Oh, that 5 smells nice. Numbers don't exist as concrete objects. But there are reasons to want to know how many of something there are. Someone might want to know, if I go to bed at night, do I have the same number of goats in my herd as I have when I wake up in the morning? How many bushels of grain do I have to give to the king as tax? These are the reasons why numbers are invented. And so we know that the words for numbers, in fact, go back literally for thousands of years, which means that the ideas, these are not new ideas. If you speak a language besides English, and if it's a language that is from Europe or India, most likely that language's words for numbers actually have lots of similarities to English's words for numbers. For example, 3 is a nice one to use. We have 3 in English. We have drei in German. We have tre in Swedish. We have trois in French. We have tres in Spanish. Notice there's some similarities here, including that the second sound in each of these words is the sound R. R, d, r, t, r, t, r, t, r. In 4 of the 5 cases, we have something that, at least spelling-wise, is really similar. We have either a t, a th, or a duh at the start. And there's actually reasons historically why what was a t sound changed in English to th, and changed in German to duh, and stayed t in North Germanic languages like Swedish and Danish and Norwegian. These languages come from similar sources. I mean, all of these 3 languages, English, German, and Swedish, have the same ancestor. They have a called Proto-Germanic. More recently still, French and Spanish have the same ancestor, Latin. But beyond that, all of these languages, along with Russian, along with Greek, along with Sanskrit and other languages of India, along with classical Persian, all have a similar ancestor that was spoken probably 4,000 years ago, something like that, 5,000 years ago, give or take. And the fact that these numbers, the words for numbers, are all really similar in these languages, just like words for lots of family relationships, like the word for mother is very similar. It usually, in fact, starts with the letter M, whether you're dealing with Latin or Greek or English or Swedish or German or Spanish or French. Were clues used to to hypothesize. This is inductive reasoning, to hypothesize that these languages have a common ancestor. And the fact that these numbers are so old are reflective of that. In other words, the numbers for 3 are really similar in all these languages, or the words for 3, I should say. The words for 0 are not, as I mentioned. They're similar in some of them, but they aren't They aren't as similar in all of them. That's because 0 is a much more recent invention. Who invented 0 is a matter of a lot of debate. Mathematicians and historians get into arguments about it for a bunch of reasons, some of which are cultural, some of which are just as what my research says. The Mayans invented 0. The Mayans had this idea of 0. And the ancient Indians in India also developed the idea of 0. I shouldn't say ancient, the classical Indians. This was not ancient times in that region. But some people will argue that the Persians actually invented it before the Indians did. In either case, the invention wasn't thousands and thousands of years ago. Now, it was more than 1,000 years ago. But it was within the past 2,000 years. So it wasn't like in the mists of prehistory. 0 is a modern idea. In the next unit after this one, we're going to talk about Roman numerals a little bit, which you've seen before. And you know that when you write Roman numerals, there's no 0 involved in it. This doesn't use our ideas of place value. Again, that's because Roman numerals, the Romans had no concept of 0 as a number. They might have a concept of 0 as the absence of something. And that's a problem with 0. It means more than one thing.
Are we being tested on this?
Nope. You are being tested on what the natural numbers are. And the natural numbers are natural because they don't include 0. 0 was an invention. And that's why they're called natural. They're called the counting numbers because when we learn to count as little kids, we don't count starting 0, 1, 2, 3. We count 1, 2, 3. If, you know, a little kid goes to count the pennies in her hand and she starts counting, she will eventually go 1, 2, 3, 4, 5. Let's say I have 5 pennies. She doesn't count 0, 1, 2, 3, 4, 5. I have 5 pennies. So the natural numbers are numbers that start with 1 and they keep going and they get bigger and bigger and bigger. They go to millions and billions and trillions and quadrillions and quintillions and sextillions and septillions and octillions, and they never end. They do not include 0. They do not include any negative numbers. They do not include any fractions or decimals unless the fraction could be simplified to a natural number. Like 4 over 2 is 2. That's a natural number. But 1/4 is not a natural number. 0.25 is not a natural number. The natural numbers or the counting numbers are always represented with the letter N as their set. And specifically in your textbook, usually it is a bold-faced N. Sometimes in Canvas or other things, it'll just be a capital N. Depends on how the formatting looks. You might in other textbooks or in the supplementary material, supplementary videos and stuff, you might see it look like this, which is sometimes called a hollow N, where you have like the diagonal part is open. That's also sometimes used to represent the natural numbers. So when you see this or this, what you should think of is that these are the numbers 1, 2, 3, 4, 5 that go on forever and ever. And that's what the ellipses means here. The ellipses here means that this sequence of numbers goes on towards infinity without ever actually hitting it. So let's represent those sets using the roster method. Set A is the set of natural numbers less than 5. What would I put in my braces?
One, two, three, four.
Would I put 5?
No.
Why not?
Doesn't say equal to.
So it's less than 5, exactly. Set B is the set of natural numbers greater than or equal to 25. What would I put in my braces?
$25 and up.
The 25 part's right. I would put at least 3. And then I put in ellipses. Letter C. We have the set of all, set E is the set of all elements X, such that X is an element of the natural numbers and X is even. What's the first number I'm going to write here?
2.
Right. So again, I'm going to write the first 3 or 4 in the list. And then because the even numbers go on forever, I put my ellipses at the end and my closing brace. Questions? Okay. The next thing I want to talk a little bit about, I'm not going to spend a lot of time on this because you've seen this before. I'm going to spend a little more time on what it looks like in set builder notation. Your textbook talks in this section a little bit about inequalities. We're going to talk about inequalities in more detail in chapter 6. We're going to solve linear inequalities while we're solving linear equations. Remember, there are 4 inequality symbols. These are these symbols here that I'm circling: less than or equal to, greater than or equal to. Those are all things you've seen a million times before. In math, what we use often is we are using these symbols in set builder notation. And you saw that in the last example about on the previous slide here for C here for the even numbers. So here, for example, in set builder notation, we have the set that contains of all elements X such that X is a natural number or X is an element of the natural numbers and X is less than 4. Here, natural number, X is less than or equal to 4. Natural number, X is greater than 4. And then on the right, we see what that would look like as a roster method. Pretty straightforward, I believe. A little trickier are when your textbook calls these multi-part inequalities. They're often called compound inequalities in other sources. One thing I want to point out to you, because it's the most common mistake I see when people do this, when you try to take this from words and put them into symbols. For inequalities like this, particularly the simple ones we're going to deal with in this book, in this course, the inequality signs are always going to point in the same direction. The words don't always indicate that. Like here in words, we could read this as X is greater than A and less than B. And so students sometimes will try to write it like this. X is less than A and less than B. And that's not right. The only way, I guess I shouldn't say the only way, the way that's most commonly used is this. You could also logically write it like this if you changed each sign and changed the order. X is less than B, but X is greater than A. I usually, when I see this, will just read this as A is less than X, which is less than B, which I think is more straightforward. But again, if you're seeing this, it can be tricky of how to put these words into symbols. So I'm just going to draw your attention that 2.1 in your book talks about this, and it's a good place for you to look for examples of that. So using some of those examples, again, we're going to look at the roster method here. So let's call this set A. Set A is the set of all elements X, such that x is a natural number and x is less than or equal to 100.
Can you mute your mic, please?
So what would go here? X is a natural number. So what's my first number going to be? What's the smallest natural number?
1.
1. So x is a natural number and it's less than or equal to 100. So I'm going to write out my first 3 or 4 natural numbers, 1, 2, 3. I'm going to put in ellipses, 3 dots, and then less than or equal to 100. So I'm going to put 100. There I have this in roster formation, or in roster using the roster method. And so we'll call B set B. Set B consists of all the elements x, such that x is a natural number, and 70 is less than or equal to x, which is less than 100. So what would my first number be here? Would it be 1? No, it certainly wouldn't be 1. So what would it be instead of 1? It's going to be 70, exactly right. So again, I'm going to write about the first 3 or 4. I'm going to put my ellipses, a comma, should put a comma up here too, and then notice less than 100. So my final number there is going to be 99. Questions? All right. Is this the last thing? I think it is. Yeah. The last thing we're going to talk about today is cardinality. Cardinality means how many. The cardinality of a set is how many elements are in a set. So if I have a set that has the elements 4 and 5 in it, the cardinality of that set is 2. There are 2 elements in the set. A key thing about cardinality is that the elements have to be distinct or unique from each other. Excuse me, 4 and 5 are distinct and unique. So that's fine for us to say. You might see this in several different ways. It might ask you, what is the cardinality of the set? It might ask you, how many elements are in the set? It might ask you, what's the cardinal number of the set? Or it might just say something like, set A equals 4, 5, find n of A. If you see n and a parentheses in front of a set like this, this always means cardinality. And cardinality is always a number. It's always a whole number. We talked about the natural numbers. The whole numbers are the natural numbers plus 0. So the cardinality of a set is always going to be a whole number, 0, 1, 2, 3, etc. It will never be a fraction. It will never be negative. And when we see this symbol, n of A, for example, that is telling us to find the cardinality of set A. Or if we're told n of C equals 8, that means there are 8 distinct or unique elements in set C. If set D contain the elements A, B, C, D, E, what is n of D going to equal? It's going to equal 5 because there are 5 distinct elements in set D. If an element is repeated, it does not change the cardinality. A here consists of 4 and 5. Let's say that set F consists of 4, 5, 5, 5, 5, 4, 5, 5, 4, 4. What is the cardinality of set F? It's still 2. It doesn't matter how often an element is repeated. We're only looking for distinct elements. There are 2 distinct elements in set F, 4 and 5. The cardinality of set F is 2. N of F is 2. The cardinal number of set F is 2. A common mistake that people make is they forget about this and they count and they say, oh, there's 3, 6, 9, there's 10 in that set. We're only interested in distinct or unique elements. What's your question?
You're looking for a frequency pretty much in cardinals.
You're ignoring frequency. You're just seeing everything that shows up once or more.
Okay.
So here we have some pretty straightforward examples. Set A, we would say that n of A, or its cardinality, or its cardinal number is 4. There are 4 distinct elements. Set B, its cardinality, or cardinal number, or n of B is 1. There is 1 element, the element 0. Here's a problem that people often get wrong. When we're asked, what is n of C? So because people often get it wrong, I'm not going to ask you to answer that because I want to put you on the spot. But I'm going to tell you that what people normally do is they subtract and they say, oh, 23 minus 13 is 10. There are 10 elements in set C. That's an entirely logical thing to do. But if you were counting this by hand, you would see that there's actually 11 in the set. And so whenever you see a set like that and your immediate thought is to subtract, that's fine, subtract away, but add 1 to your final answer. So there are 11 elements in this set. And then our final ones, whoops. Set A, set of all elements X, such that X is a month of the year, n of A equals 12, because there are 12 months in the year. B is the empty set. As you might imagine, the empty set has cardinality 0. And then set C, Y is a natural number. 5 is less than Y is less than 8. So if we were writing that out, which is helpful in a problem like this sometimes. So Y could be either 6 or 7 because it's a natural number. We aren't looking for decimals or anything like that. And it has to be greater than 5 and it has to be less than 8. There are 2 natural numbers that meet that criteria. So n of C equals 2. Again, the most important thing to remember about cardinality, the 2 most important things are sometimes you're just going to see this notation, and that means cardinality. And when we repeat something, we count it only once. So if I have a set that has 2 6s, 3 7s, and 1 8 in it, there are 3 distinct elements in that. So the cardinality of that set is 3. There's 6, there's a 7, there's an 8. It doesn't matter how often something is repeated. That's going to be important for next class, because in next class, we're going to talk about equivalent sets. And you need to know cardinality to understand equivalence. And then from equivalence, we're going to talk about equal sets. I've just put in the chat the attendance and participation link for today. Please fill that out. If you cannot access it, please send me an email. I'll check my email immediately after class and email that to you if you need it. Remember, homework and quiz are due at the end of the day if you haven't already turned them in. If you have a question about it, please, please, please send me an email and let me know. Remember, if you send an email in the evening, you might not get a response until tomorrow morning. Have a good long weekend. Have a safe Labor Day. I look forward to seeing you in class on Tuesday again. Are there any last minute questions for me? Hearing none. Once you're done filling out the form, go forth. Have a great day. Have a great weekend. Do great things. Enjoy your homework. Keep it real.